All right, in this experiment, we shall be looking at crystallization. So a substance is crystal if its molecules are arranged in an ordered manner, whereas a substance is non-crystal, also called amorphous, if if uh, if it is if it is if its molecules are arranged in a disordered manner. Whereas there are compounds also that contain a group of compounds which are ordered, which the molecules in each group are ordered, but overall the compound has some irregularities, and that we call it polycrystalline compound. Examples from real life: the sugar is a crystalline substance, whereas powdered sugar is an amorphous substance where supposedly the molecules of sucrose in the powdered sugar are supposed to irregularly arranged. So the name crystal stands for such substances, whereas the process of forming crystal is called crystallization. So the most important thing in crystallization is selection of a solvent. Different solvents have different polarity. That's why they can dissolve different compounds, because different organic compounds have also different solubility because of their polarity, the similarity to that of the solvent. So polarity in chemistry is separation of electron charges leading to a molecule having an electric dipole moment, and this electric dipole moment is usually taken as a measure of separation of positive and negative electric charges. So the more the dipole moment of a compound have, the more polar compound it will be. On the other hand, dipole moment of a compound is also related to dielectric constant, and similarly, more dielectric constant of a compound means the more polar the compound will be. And the dielectric constant is usually represented by the rho symbol. I think that it's a rho symbol. And in general, like dissolves like, which means polar compound normally and usually also dissolves in a polar solvent. However, this can be affected by temperature of the solution or the environment for that matter. Examples of solvents beginning from water, which is the most polar solvent we have, and to simply distinguish the polarity of water is to see the charge separation between oxygen and hydrogen, where the electronegativity of oxygen is 3.5 and the electronegativity of hydrogen is around 2 or 2.1, and you can see this large separation results in having large charge separation, and then in creating large dipole moment that makes the water more polar and also suitable to dissolve these polar compounds, because if you see the compounds contain OH, which is a polar bond, which can be better soluble in polar solvent like water. Dichloromethane is a moderately polar solvent, where you can see the two chlorine atoms have a net dipole moment, but they can also cancel to each other somehow, and they are suitable to dissolve alkaloid compounds like caffeine and nicotine. Hexane, a hydrocarbon compound containing carbon and hydrogen, is an example of a nonpolar solvent, which is suitable to dissolve a class of lipid compounds and compounds such as jasmine and tetradecyl pentadecanoate. It's a compound which is one example of lipids actually, which is a component in wax. So in this experiment, crystallization is performed as an experiment to purify a contaminated solid. To do this, the first procedure is to select a solvent. So in addition to the theoretical background, experimentally, a suitable solvent for crystallization experiment is selected based on this simple experiment. You add your solid substance, the impurity, and you add some amount of the chosen solvent. If the solvent dissolves that substance at room temperature, it's not regarded as a suitable solvent. Whereas if the solvent dissolves that substance when it is boiled, then the solvent will be regarded as a suitable solvent for that substance. In regard to this, the solvent is expected to dissolve the impurity while cold, but do not dissolve the target compound while cold, which means when we dissolve them together while hot, the solvent will dissolve both the solid compound and the impurities, which will later be separated by simple filtration. So the crystallization experiment looks like this, where you will add a hot solvent into the solid impurities and allow the solution to form, which will take some time, and you need to carefully watch if all the solid material is dissolved. You then cool the solution for allowing crystals to form, and then you can then filter it and get your crystals. So in this scheme, you do only see cold filtration. However, in between these two, in between the second and the third, we do have hot filtration. That's done because the insoluble solid impurities should be separated first during the hot filtration, which we will be looking at in the actual experiment. So in this experiment, you'll be taking 0.5 grams of impure benzoic acid and then add 2 ml of water and heat the solution on hot plate or on a heating mantle, it doesn't matter. So it's wise to add not all of the 20 milliliters, because later on you may add some amount of water to make sure that all the solid substance dissolves. And then once the solid substance dissolves, you can cool the solution. You can cool the solution and then allow for crystals to form. So actually, in this step, once you dissolve the solid substance, it will be hot, so you have to gravity filter it, which is not shown here. I think it will be shown in the next slide, and that is for the purpose of separating insoluble impurities. It could be insoluble chemical substance, or it could be broken glass or dust for that matter. And then you cool your solution to allow crystals to form. Sometimes crystals will not be formed because your solution is too dilute. You have excess solvent, more than 25 milliliter, And to avoid this or to address this, you have to keep heating the solution until the solvent evaporates, leaving around 25 milliliters of solvent in the flask. Or if this technique doesn't work, you can scratch the walls of the Erlenmeyer flask so that the droplets of the scratch will be used as a seed for the crystal growth. You can also make ice cooling. You can put the flask in ice baths to initiate the crystal growth. So once you see your crystal formed, the next procedure will be to filter the crystal slowly in a cold filtration. The cold filtration setup is a Beechner funnel with attached to a suction Erlenmeyer flask, where the suction Erlenmeyer flask is connected to vacuum pump, which the filtration is not only gravity filtration, but because the vacuum sucks air from outside and the air has to be pushed through the Beechner funnel. In that way, it will dry out the crystals in a cold manner. It's just to dry a clothes by a wind when there is not sun, actually. So then you'll have crystals. Finally, you can dry out your crystals. In fact, here you have to be careful in obtaining the pure benzoic acid crystals, because the crystals are so light and they can float and they can give you wrong weight when you calculate the percent recovery. But your final task in this experiment will be to calculate the percent recovery by the formula you see in the slide, which can be done by just dividing the final weight of the crystals you obtain after crystallization by the initial weight of the impure solid substance you got, which is 0.5 gram, and you multiply that by 100, and that will give you the percent recovery. Safety issues in this experiment. So the leftovers of benzoic acid or the benzoic acid you crystallized, it will be a waste after you calculate the percent recovery, and the filter papers that contaminated with this chemical will all be solid wastes. Any broken glasses, any beakers, or any broken glass for that matter while you do the experiment will be put to a glass waste container. And all liquids, normally the water solvent liquids, are supposed to be contaminated with benzoic acid, and they should be stored in aqueous waste containers. And then, because when we measure the benzoic acid, we will be using balance, and the balance area should be clean for any droplets of that substance.